I'd like to thank the organizers, of course, for inviting me to Bonn. It's a pleasure to be here. Of course, when I got the invitation, there was a description of the kinds of things one should be talking about. And in particular, you should talk about something that you don't know anything about. And the more I thought about what I didn't know anything about, well, I came to the conclusion that maybe Weyl sums, I thought I knew something about, but maybe after all I know less about this than anything else, because I know less about this than anything else. If I talked about some other topic, I might not know that I know less about this. There's some logic in there somewhere. So really what I want to do is to try to explain how pathetic our state of knowledge is about Weyl sums. So this is slagging off all my colleagues, all my ancestors mathematically, and complaining about how little we know. So, let me try to set the scene. And of course, the subject is big, so necessarily you have to narrow down the range of topics. So the general thing that you might look at might be an exponential sum, and I'm going to specialize this exponential sum for the sake of discussion to a simpler version. So maybe you might be interested in sort of the Vinogradov exponential sum, and as usual, use standard notation. And here we have in mind that n is a large positive integer, probably, and alpha 1 up to alpha k are coefficients, real numbers, and we're summing over polynomial values. This is what I'll be focusing on. And for us, in this talk, I'm going to specialize to just a one-variable version of this, because this is enough to illustrate ideas. So I'll just look at K powers, and everything that I say pretty much can be extended to the more general situation. And there's a secret tool that professionals in the circle method use and doesn't occur in any book. And I always explain this when I teach a course on the circle method. So if you want to understand these exponential sums, there's something which I refer to as the circle method complexity of a real number alpha. And what does it look like? It's some kind of height. I call it a complexity because height is overused. It depends on alpha, of course, and it also depends on the length of your sum and the size or the degree of this polynomial term. So you could think of it as depending on n to the k in this context. And this is just the min over all integers a and natural numbers q of q plus n to the k q alpha minus a. Right, so what's going on here? Well, if your real number alpha has a rational approximation with small denominator q, then you can expect that if the rational approximation is good, this expression is going to be relatively small. This is what you typically see on the major arcs in a circle method approach. And on the other hand, if alpha just doesn't have good rational approximations with q relatively small, so q is automatically relatively large, then this expression is going to be large. So it measures, in that sense, the complexity of alpha. But this is not just some kind of heuristic tool. So if you use Dirichlet's approximation, you can always find, if I give you my favorite alpha, you can always find a rational approximation where this object is relatively small. So let's say there exist integers a, natural number q. I can always arrange that q is at most as big as n to the k over 2. And with such a choice, I can arrange that Q alpha minus A is almost as big as n to the minus k over 2. That's just Dirichlet's approximation theorem. So that means that always h of alpha is almost as big as, or if I sum these two terms, in this situation it's almost as big as twice n to the k over 2. So this complexity is limited. And also, this is one observation. The second observation, so if you know that h of alpha is, let's say, some parameter capital Q in size, then there exist integers a natural number q. You can, of course, arrange that a and q are co-prime with the property that q is less than or equal to capital Q, and q alpha minus a is almost as big as q n to the minus k. So this is exactly the kind of situation that you might want to use inside the circle method. So this h of alpha really determines what's going on. It's the natural object to look at. There are different ways one could arrange this. Maybe you could take look at the maximum of q and n to the k q alpha minus a, which might be more natural. But this is a good measure of the complexity of the situation that we're facing. So I can sort of phrase one basic question in the subject, which is just to understand the behavior spelled with a U of an exponential sum like f of alpha for this height in the full range. This is the basic question of the subject. Understand what happens at any choice of alpha. So I want to, sort of talk a little bit about what ranges of h of alpha we understand well, and what ranges we know prophetically little. But if you have in mind this measure of how complicated alpha is, then that sets the scene. Anybody want to complain about h of alpha?
About what?
About h of alpha.
I mean, you could call it the conductor.
The conductor of that would also be an overused word, yeah. Right. So you don't find this in any book, but if you learn about the circle method, you know this, even if you didn't recognize that you knew it. Okay, so so the three, what I think of as being trivial ranges for h of alpha. Okay, so, I mean, one is the most trivial of all, and therefore it's 0, case 0. So what happens if h of alpha is bigger over 1 somehow? So then what we're thinking of is alpha minus a over q maybe is almost as big as 1 over 100, n to the minus k, and q almost as big as 100. Something like this. You could think of q as being 1. This is the simplest situation of all. And then, well, it could be that f of alpha is actually 0, possibly. But typically, well, there are many situations at least where f of alpha might be as large as n, simply because there's essentially no cancellation in the exponential sum at all. So this is something which is well understood, and nobody gives you any prizes for thinking about these things. So it's not just around the origin, and not just around alpha equals 0, or alpha very close to an integer where the exponential sum might be so large it's at all rationals which have very small denominator where this phenomenon might exist. Okay, that's the trivial case. So what about the range where h of alpha might be as large as n. Right? So remember, the full range for h of alpha goes up to n to the k over 2. And for this talk, I want to think in terms of k as being relatively large. Some of my analytic number theory, I was going to say friends, colleagues, really think only about quadratic forms. They're entitled to think about such things, but I'm less excited about quadratic forms than higher degree forms. That's where all the challenges are, in my view. So, so what happens in this situation? This is very small, isn't it, if k is large? Okay, so so this is really where the subject started somehow with Hardy and Littlewood in the 1920s. And I wanted to, if you've studied the circle method, you know this argument, but if you haven't, maybe it's useful to just indicate roughly what goes on. So in this situation, you use the mean value theorem. What we can do to simplify life a little bit is write alpha as beta plus a over q. And here, a and q are what would be specified by this height condition. So I'm thinking of a uniquely associated a and q associated with the height. And then how do we analyze f of alpha? Well, well, what I should do is break up the range of summation into arithmetic progressions modulo q. And I've got enough space here to do this. So now I'm summing from r equals 1 to q. And I want to think of x as being q times y plus r. So then this range for y, really it doesn't matter precisely what the endpoints are, maybe y goes roughly up to n over q. And the reason this is useful is because alpha is close to a over q, so it naturally detects these arithmetic progressions modulo q, doesn't it? And the point here is that the multiples of q here don't see this a over q term. So this naturally simplifies. I get some expression involving a over q r to the k. And then I've got some other expression which has an argument which is small, right? So beta is almost as big as 1 over q times into the 1 minus k maybe, because h of alpha is sort of tiny, but beta is very small. Times stuff which looks a little complicated, but you can use the mean value to estimate this. Because beta is so small, and if you work this out carefully, which Hardy and Littlewood did, then you can rewrite this in terms of an integral, sort of, this is why the mean value term is involved. So it's a nice exponential integral, and the error term that you get here is something which is easy to work out, something like 1 plus n to the k absolute value of theta. So the upshot of this is that this exponential sum, which we started with, in this situation where the height is relatively small, only going up to n, you can write down a main term for this, which I use some notation for. So S of QA is a Gauss sum. And d of theta is this exponential integral. So that's a main term, and then there's an error term which has size which looks a lot like the height, this height function which I looked at, this h of alpha. So if I've chosen a and q consistent with the height function, And you can see here that this expression here is no bigger than the height, and in particular, if the height is at most n, then at least this stands a chance of being a non-trivial estimate, because the trivial size for the exponential sum, the trivial estimate would just be n. Now, there's a key aspect of this which I made use of, which is going to be a recurring theme, and part of my theme of being unimpressed by all the estimates that we have, which is that we used congruences modulo q here, and the reason this argument worked at all is because the length of the exponential sum is larger, or at least as large as the congruence constraint. Of course, if you look at congruences modulo q with variables which are bigger than q, then you can just break everything down into congruence classes and hope that you estimate everything by just looking at individual congruence classes. It's a nice idea that Hardy and Little would exploit it, and there we are, we've got some asymptotic for this exponential sum in this range. So of course, one can do a little better than this, and this is in some ways consistent with something I think that Emmanuel mentioned yesterday. So you can use Poisson summation to refine this estimate. What you can do is use Poisson summation to investigate this inner sum here. And if you do that, then you get to refine this estimate, which we just sketched, this way of proceeding. So if I subtract the main term from f of alpha, then the upper bound that you get is like the square root of this height function. So here again, a and q are associated to alpha via the height function. And so now this extends the range where you get non-trivial estimates, doesn't it? So maybe I can grab some more space here. So, so pretty clearly, this allows the possibility to extend the range where you have good control of the exponential sum from height up to n to height up to almost n squared. And if you're interested in quadratic Weyl sums, which some of my colleagues are, as I mentioned, then because the height is never any bigger than n to the k over 2 size, which is n when k equals 2, then you've got very good control of everything. You know, the error term involved here is something like the square root of n, which seems pretty good. But if k is big, then this situation is not so good, is it? I mean, if k is bigger than 4, then this error term is worse than trivial. So the uniform estimate that you extract from this is something like n to the k over 4 plus epsilon. And if k is bigger than 4, as I said, this is worse than trivial. So, so that's bad news in some sense. But what this does show is that at least in the range where h of alpha is almost as big as n, then the error term is good. And this is enough with work to show that the contribution in mean values arising from these alpha of small height going up to n, you can get an asymptotic formula for this kind of thing, which certainly shows that this mean value has size big O of n to the s minus k plus epsilon, when s is at least as big as k plus 1. And just to emphasize, if S is k plus 1, this is way better than square root cancellation, isn't it? This is, you really know everything that you would like to know about this. So, okay, so that's the good news, right? And the good news involved breaking into congruences, and if Q, the size of these denominators, which is related to this height function, is much bigger than n, then this is something which is difficult to envision. Okay, so maybe just to finish up this initial line of reasoning, because I'm likely to ramble about this if I'm left to it. So, so I should mention that Vaughan had what he would like to call speculation, which he says is not a conjecture, it's just speculation. Well, what he speculated was that f of alpha minus this main term should be bounded above by what I'm paraphrasing, because he did not use this height function, but h of alpha to the 1 over k plus epsilon uniformly in this height. Good, and remember h of alpha can be as large as n to the k over 2, so this would be like square root of n here in the worst case, but usually much better. And this speculation was shown to be false in work of Rudin and Damon. This was published in 2009. So there's much more that is proved in this work, but in particular, the difference between this exponential sum and the main term is greater than square root of n for almost all alpha. This would be one way to loosely paraphrase what is proved. And in particular, even for almost all alpha where the height is not too big. So clearly this speculation of Vaughan was a bit too speculative. And so I think the conjecture that most people would believe is that this difference between f of alpha and its main term is less than square root of n for all alpha, height going up to n to the k over 2. And of course it can be smaller than this. We've got an estimate which lies directly above this, which shows that when h of alpha is very small, then you can do better. Okay, so the challenge problem is to take k large, take q to be, let's say, n cubed in size. I mean, I'm not being very ambitious here. N cubed is bigger than n squared, not much bigger. And now try to estimate the difference between the exponential sum where I just make it a rational number with denominator q, and I subtract off what you would imagine would be the main term here, and you want this to be smaller than n to the theta, and you want theta to be smaller than k over 4. And since k over 4 is not that ambitious, if k is large here, then I want this theta to be independent of n. Independent of k, sorry. Strictly smaller than 1. So we'll see that you can get estimates shape where this theta is smaller than 1, but in a way which depends badly on k. And this is not exciting for me. Well, okay, it's reasonably exciting. It might be exciting, but not in a way which I can advertise it.
Trevor,
Yeah.
the first line for h alpha less than or equal, I thought h alpha is always less than or equal to 2 times.
H of alpha is always almost as big as 2 times n to the k over 2.
Right, and that means your conjecture is this holds for all alpha?
For all alpha, yeah.
For all alpha. Okay.
Yes. You can write that down if you prefer, that's fine. Yeah.
Sure.
Yeah. As opposed to the estimate on the...
And Trevor, in your challenge problem, the implied constant in the less than depends on k.
Oh yeah, so
k is
I would be quite
fixed.
happy if this depends on k. It should be, the focus is on n. Yeah, yeah. Okay, so I wanted to indicate how pathetic our approaches to this problem are. So I've shown you one approach to this. We've had a century to think about this problem, and what we've done in a century is, on reflection, hardly any different, or hardly a little bit did. We have one idea which recurs in various different styles. It gives different results, it's true, but it's all the same idea in disguise. And so maybe one of the themes for this first part of the talk is that one should avoid using this idea because there's got to be another idea. And the idea is well tested. So how little we know. So what are the different approaches to handling this problem? So I'm going to focus on the exponential sum f, but I'm going to stick to looking at rational numbers just because we don't really lose anything by looking at these rational numbers. Okay, so the oldest approach is to use Weyl's inequality. And as expected, I'm using more time than I would like, so I'm going to be relatively brief in this. So what Weyl's inequality does is to lower the degree of your polynomial. You make use of the fact that f of alpha squared I can write in terms of a forward difference operator. And you can think of this as being associated with a polynomial of degree k minus 1. So if you repeat this enough times, then you reduce the degree of the polynomial to 1. And the kind of estimate that you're able to obtain if you apply Weyl's inequality, repeated application of Cauchy-Schwarz, is something like this, and this certainly gives the right flavor. So I separate out a term corresponding to where these difference variables, one or more of them might be 0. I end up with sum over x in some interval, an interval of integers, and then the upper bound that I get involves x only linearly. I've got all my difference variables, which occur as a nice product, and some other stuff, which is actually just a sum of h's, but is not really relevant for this estimation. And we all know how to sum a geometric progression. And so the upper bound that you obtain from this process makes use of a divisor estimate, because the number of ways you can write an integer as a product of integers is small. So it's n to the epsilon factor. And then I have a long sum over some variable which I'm calling little h here. And the sum over x can be replaced by this min of trivial estimate n, the length of the interval, and the distance of h times a over q to the nearest integer. This only depends on h mod q. Notice it doesn't depend on anything else. Now h is in the long range, so what we essentially did here was we found an elaborate way of gluing together lots of copies of the variables x in a way that we got a big integer, which is big enough so it doesn't matter how large the modulus q is, I'm able to think about congruences again. Which is what we did before, isn't it? We wanted to have variables which were long enough that we understood what happened when we reduced mod q. Okay, so we had an idea which is gluing together variables to make longer variables. And if you analyze this carefully, you can estimate this kind of thing. You find that the estimate that we get here, and here I'm specializing to f of a over q, as I promised, to make life simple. The estimate that I get is non-trivial. For q going up to whatever my widest range is, it's actually non-trivial for q at most as big as n to the k minus 1. But it has a pathetically weak exponent here, doesn't it? So it's exponentially small. So, so this is what Weyl did even before Hardy and Littlewood's work in the 1920s. And you can see the same idea recurs, doesn't it? We're using congruences again, it's just we found a way to use congruences but glue together variables to make things long enough. So if we were to use this in these estimates, I look at f of alpha minus its expected main term, the main term for much of the range would be much smaller than this. So you can kind of obtain an estimate where maybe you win this n to the 2 to the 1 minus k over the trivial estimate in our upper bound. This is very far away from what we would like to be able to prove.
Your last line is not quite normalized.
It's not, that's right, yes. This is a 2 to the k minus 1, thank you.
Yeah, and then
then you can read off exactly what happens. Thank you. Yeah. Okay, so that's one different approach, which is almost the same approach. Let me mention two more approaches, which are also essentially the same approach in disguise. So of course this alternate approach due to Vinogradov. And maybe I think of this as the first Vinogradov approach. And there are various ways of setting up this approach of Vinogradov, they more or less amount to the same thing. So I'm going to choose one which sort of is easiest to describe from first principles. And it's slightly wasteful, but it illustrates all the right ideas. So what we could do is look at the square of this exponential sum f of alpha that we started with. So this is a bit like a Weyl differencing step. But the merit of this is that we introduce an almost bilinear structure to this expression. It's not bilinear yet, is it? Because in the dots here, there are all kinds of expressions involving powers of h. But I've got two variables to play with. And what I can do now is to look at a large power of this expression that I just wrote down. So if I use Holder's inequality, then what I can do is glue together variables again. Right, so I've got a 2s power of an exponential sum over x on the inside of this expression. And so if I expand this rule, I can think of it as a sum over 2s variables. And these expressions, which I define in a moment, and maybe I'll still keep an absolute value here. So these expressions on the inside here are sums of powers and as I look at the binomial expansion, the stuff in the dots, I'll have different powers occurring. And so the idea that Vinogradov had, of course, was to look at equations defined by simultaneous equations of this type, counting the solutions of these things. So if I use orthogonality to understand the number of solutions of equations where I represent some k minus 1 tuple of integers L sub j, then if you play around with this, cutting out all the details, but the kind of thing that you can expect to obtain as an upper bound is n to the 2s minus 1 still, remember. I have to fix choices of L1 up to Lk minus 2. So there's some cost to doing that. And then there's the number of solutions of a system of simultaneous equations, which I encode with this expression, which I'll define in a moment. And then there's an exponential sum that I get to estimate from all of this. And so this L you can think of as being like the Lk minus 1 expression here. So something like this, where this mean value js k minus 1 then is just counting the number of solutions of the system of equations having degree j running from 1 up to k minus 1 with the variables almost as big as that. So it's sort of a more complicated endeavor to get into all this. But the whole point of this was to glue together variables again, to get a long variable and another average, where we're, again, alpha is, I'm thinking of as being a rational A of a Q for simplicity here. So now I can think about what happens when I reduce this long variable modulo Q. Well, This looks a lot like what we got from the Weyl differencing step. In fact, it looks uncannily like what we got from the Weyl differencing step. It's just that if we understand this mean value well enough, then we don't have to use 2 to the k variables to get here, or 2 to the k minus 1 variables. We get to use something which goes just quadratically, grows quadratically with n. And in the current state of the art, we're able to get away with something like k times k minus 1 variables. This is, of course, work of Morgan, Vinogradov, and myself. But you can see, okay, so we've reduced the number of variables we had to glue together, but it's exactly the same story in terms of getting an upper bound for this expression f of alpha. And if I glue together all of these estimates, then what do we find? We get an upper bound which is exactly the flavor of what we had before, just with a slightly better exponent. Let me get rid of Wooley here. This is easy to do. So still pathetically weak, and using exactly the same idea, just in a different disguise. Okay, so in the interest of time, the third approach, which I won't say so much about, I'll kind of say it in more or less in words, which follows a similar theme, and that is what you can think of as a bilinear approach. And this occurred in the talks of Emmanuel and Philippe yesterday. And that is to introduce a bilinear structure more or less from the beginning. And so this is an idea which occurs repeatedly in Vinogradov's work. And is explained in a different sort of format by Bombieri, attributing it to Korobov. And that is to replace the initial exponential sum that we have. So of course we start off with an exponential sum in k powers of x. And what we could do instead is shift these variables x. We're still in an interval here, so we're not too ambitious about how to use these shifts. If we don't make them too long, then we get an acceptable error, and we can average over these shifts. And if we do this, we can choose any structure for the shifts we like. And if you use a bilinear structure, then you get to expand this, glue together copies of u and glue together copies of v. And if you do this, you find that the kind of estimate that you can obtain by following the natural approaches we've seen would look something like this, to the 1 over 4s squared. As soon as s is big enough that you are able to control the mean values of exponential sums, things like the Vinogradov mean value theorem. And this, in fact, in the current state of knowledge, doesn't improve any exponents at all. In former times before the main conjecture in Vinogradov's mean value theorem was proved, this gave you some modest improvements. You saved some logs, but now it's no longer so important. And again, when you do this, you end up with expressions very similar to what we were looking at before. The whole goal is to get intervals of integers gluing together, which are big enough that you understand congruences mod q. So all of these approaches are basically the same approach. And that's why we have pathetic estimates. Yeah.
So this seems to be a little worse.
Sorry?
This seems to be worse in the exponent of k.
I mean, certainly for pure k powers, it is worse. The Bobbieri-Korobov method is really designed to look at these expressions where you have a full Vinogradov sum. And there you actually get to glue together the contributions from different powers. And so in former times, what this would give you is an exponent which was something like 1 over constant k squared. These days, thanks to the resolution of the main conjecture of Vinogradov's mean value theorem, we already get 1 over k squared even from this older method, so it's really not so relevant. Okay, so this is sort of a pointwise bounds for exponential sums. And you can see, I hope to convey, there's one idea here, which is thinking about gluing together variables so that when you look at what happens mod q, you actually understand the congruences. And that's the only idea in town somehow. I mean, all these ideas for gluing together variables are incredibly inefficient. So the challenge problem, as I said, is to find a method which avoids all of this and still gives non-trivial estimates for the difference between f and its main approximation. So I wanted to spend some time, and I guess I still have enough time to give an overview of this, some time on mean values. So if you can't achieve success for pointwise bounds, maybe you have more confidence about what happens when you look at mean values. And here, the nice thing about mean values is that there are sort of nice arithmetic interpretations for what happens. So maybe to illustrate ideas, I'm again going to look at this same exponential sum f of alpha. So by orthogonality, this is counting the number of solutions of an equation in 2x variables. And so there's a natural connection with points on a particular hypersurface here. And there's a long history to this problem, so we know what to conjecture for this point count, and we can prove this in many situations. Yes, so maybe actually I should maybe do this. So there's a contribution from the product of local densities. And this product of local densities reflects the contribution from what happens for the contribution from h of alpha less than or equal to n, let's say. And then there are diagonal solutions. And these correspond to what happens. So there are points on special linear subdividers here, aren't they? And what I want to do is to indicate how this connects, at least in some sense, with the previous pointwise bounds, which I was mentioning, and in particular the pointwise bounds corresponding to rational numbers with height q in these interesting situations. And there are really some nice mysteries associated with this. So, what's the overriding challenge problem? So maybe the basic question for these mean values from the point of view of the circle method worker, which all connects with harmonic analysis, is to understand the source of the various contributions to this mean value, which I defined, IS of n. Of course, that's a special case, but never mind. Arising from points alpha in the full range but h of alpha can be as large as n to the k over 2. And maybe as a challenge, and we don't even know how to do this, identify the source of the diagonal solutions and these are the ones arising from linear spaces. Right, so I can say a little bit more about this just to make this all clear. So as I mentioned there in passing, the contribution from the small height alpha, one has a good understanding of this. This is a product of local densities. So this is all the parts which we understand the associated congruences very well. So that's nice. And presumably, and this is something which was conjectured at least in some speculative appendix in some work by Bob Weyl and myself. So if you look at the contribution from these large height points, it should be asymptotic to the contribution of special subvarieties. And these linear subvarieties are certainly examples of such, but they're not the only possible example. When we examined this problem, we had in mind the particular situation of cubic exponential sum. And what we were able to show is that there's an asymptotic formula for the number of solutions, which contains a term corresponding to the diagonal contribution. And then, we were able to obtain upper and lower bounds for the residual term, which were of the same order of magnitude, and the actual asymptotic, which I've reported here, is due to Delahaye in subsequent work. But part of the analysis that we did in this appendix was to show that this term n squared log n to the fifth does actually arise from the major arc contribution. And then, I can report along similar lines. So there's work of Rudin, myself from more recently, which is sort of a more complicated situation, but again involves this cubic exponential sum. So now, instead of implicitly having two equations, one linear and one cubic, we have three equations, two linear and one cubic. And we're able to show that there's an asymptotic formula for the number of solutions where the product of local densities, which I've written C here, gives part of the contribution. This corresponds to this contribution from points of small height, and then there's a contribution from linear solutions, and these are completely separate. They don't interfere with each other somehow. So that, again, provides some kind of evidence for where these contributions arise. But there are more complicated situations where there are contributions that are not just linear. And these one also has to account for. My favorite example is the example involving an equation involving 6/4 powers, because this is sort of very simple to describe. I guess, yeah, okay. This. So this is quite a simple thing to look at. So all we're doing here is we're counting solutions of the equation defined by sum of 3/4 powers equal to another sum of 3/4 powers, with the variables all in a box of size n. And one can see by pure thought, of course, there are some solutions here which come from diagonal solutions, where x1, x2, x3 are a permutation of x4, x5, x6. There's a product of local densities in this problem, which come from these small height solutions. And this you can prove this corresponds to the small height expression, just the major arc contribution. And then there's a second contribution which you can identify, and you know exists, which has size a constant times n squared log n. And these are a little bit harder to discern. It's not as if you expect to see these until you know they exist. But if I set x3 to be x1 plus x2, and x6 to be x4 plus x5, and I substitute into this expression, you use the fact that a to the 4th plus b to the 4th plus a plus b to the 4th happens to be the square, twice the square of a squared plus ab plus b squared. So if I make this assignment, then I just have to make sure that x1 squared plus x1 x2 plus x2 squared is x4 squared plus x4 x5 plus x5 squared. And that is a nice quadratic problem. Turns out you can analyze that. The number of solutions of that in a box of size n grows like n squared log n. So definitely bigger, provably bigger than the contribution from the product of local densities, not accounted for by this diagonal at all. So it's definitely a different contribution. And the challenge for the second method, or understanding the harmonic analysis here, is where do these different contributions come from? Clearly they come from points where the height of alpha is bigger than n, but it's not obvious which parts of the domain they should come from, or if they come from anywhere. So that's really a major challenge. Okay, so I can present, just to finish up, in the last, I think I had maybe, I don't know, 5 minutes or something. So a model problem, which one can think about, which embodies a lot of characteristics that we're seeing here, and gets back to the observation that I made about the pointwise estimates all relying on understanding congruences and gluing together variables to make the variables bigger than the congruence modulus. So the model problem would be to obtain good estimates, whatever that means, for the Q analog, what I think of as a Q analog problem. And what do I mean by this? So I mean counting solutions of the mean value corresponding to 2s k powers, where I'm counting solutions mod q, and the variables are in this box of size n. So I've got this is 1 over q times the sum equals 1 to q of f of a over q to 2s. It really does look a lot like the mean values we were studying. And what's interesting for this discussion is to keep q fixed, but with q in the range which is definitely bigger than n squared, by a sizable amount even, and going up to into the k over 2. Right, so now the variables are much shorter than the modulus. This is the dangerous range when it came to making these pointwise estimates, isn't it? We had to glue together variables to make something long enough that we could estimate things. And at the same time, we can more or less think of q as being almost as big as this into the k over 2. And maybe I can stress that what's going on in this problem is that if q is almost as big as n, then this problem really looks like a congruence problem, doesn't it? Because the variables are big enough that you can just reduce into congruences. It's purely a z mod qz problem. And there's a range of possibilities. And once q is bigger than n to the k, at least, and this is a problem purely about equations. So this congruence, if q is bigger than n to the k, we're just counting solutions of equations in integers. And there's a whole range of activity in between where the problem has features which are somehow a hybrid of these two situations. And this is very much similar to what happens in the efficient congruencing approach to Vinogradov's mean value theorem, where you look at congruences modulo large powers of p, and somehow the solubility in equations is again a sort of a hybrid problem. You have lengths of variables which do not make them problems purely about congruences, they're problems which reflect features of equations as well as congruences. So it's definitely a nice sort of spectrum of sort of results to look at here. And I think my time is just about up. I don't have any theorems about this, although let's just say that there's work where you cheat and you don't look at solutions where all variables occur, but you make some restrictions on these variables and you can say something. And that's something that I'm actively pursuing with Bruden right now. This problem remains completely open.